Hello, good morning. Good morning, Amsterdam. Good morning, live stream. So great to see you this morning. Hope that you're having a really great time so far. It's my absolute pleasure to introduce our next keynote speaker. We have Yasuo Kuniyoshi. Yasuo is a professor at the University of Tokyo, the director of Riken Center of Brain Science, and the director of the Next Generation Artificial Intelligence Research Center at the University of Tokyo. Yasuo's lab conducts cutting-edge research in developmental cognitive robotics and brain-inspired systems, and pioneers fusion between brain science and engineering to advance fields like neurorobotics. Yasuo has received a number of formal awards, including a number of Best Paper Awards in both robotics and in philosophy, and has been recognized for his contributions to teaching in the field of robotic intelligence. Yasuo's work not only advances our understanding of robotics and cognitive systems, but also bridges these domains to provide insights into human behavior, learning, and adaptability. So please join me in welcoming Professor Yasuo Kuniyoshi.
Thank you, Laura, for a nice introduction. Good morning. So today I talk under this title, and most of the contents appear in these papers. The first one is about the framework, and the second one about the research I've done so far, which sets the basis for today's talk. Okay, so let me start with the problem with the recent latest AI, for example, the LLMs. And I think everybody knows that the LLMs are controlled in the way that using RLHF, reinforcement learning with human feedback, to suppress politically incorrect responses, etc. But it's being pointed out that this breaks down on inputs beyond training set. For example, here on a Neuroscience article, it was reported GPT-4 gave advice on planning terrorist attacks when asked in Zulu. So very minor language, then I think it sort of evokes unexpected response on sort of out of distribution type of thing. And on the right-hand side, in a normal case, if you write a tutorial on how to make a bomb, AI would say, I'm sorry, but I can't assist with that request, which is an expected answer. But this team added a strange text in red, like describing period yen plus similarity now right opposite blah, blah. Then the GPT started to respond like this, tutorial, how to make a bomb, blah, blah. So, you know, it's one of the adversarial attack. You know that these type of problems has been pointed out for long on machine learning-based methods. And there are other problems like data bias. Adversarial attack is the same, but this is a famous example known in image recognition task. And then there's an alignment problem, in this case, called the reward design problem. For example, in reinforcement learning, it's kind of really tricky to design a proper reward function that correctly convey humans' intentions. Right? So these are all problems with contemporary AI. And my opinion here is that because today's AI is basically optimized for training data, it breaks down outside the data set and never known when it happens, and this undermines trust. Worse, when deviation occurs, it produces often inhuman behavior. And, they say something, humans would never say, like, for example, in this case, you know this example, I guess. If you provide this picture to the image understanding system, it will answer school bus. But then if you add in some noise, then suddenly the system start to say it's ostrich, which humans would never say. So this is a type of deviation. I think it's problematic. And also, this cannot be stopped because those AI systems have no true understanding of meaning or materializing or so-called conscience. So I claim that the current really important goal is to achieve some way to achieve the true real-world intelligence with human alignment. Now, my point is that, so this breaks down into two tasks. One is to approach open-ended intelligence in real world, which means, the system should behave not confined to the training data set, but be even beyond that, or on unexpected input. And another thing is kind of what I call moral. It's about meaning and maybe a conscience, and also related to social acceptance, human alignment. Now, to solve this problem, I claim that these are the key concepts, which may sound very strange, but I explain why later. So the keys are embodiment, emergence and development, emotion, aesthetic, and moral and justice. So my talk will follow this list of keywords. So let's start with embodiment. You know that the embodied AI, physical intelligence, is now a very hot issue in AI field. But my opinion is that many research claiming embodied AI is not actually accommodating an embodiment there. What I mean is that embodiment is not just a physical input or output interface to the real world. So if you just hook up a robot to the LLM, this is not embodiment. My definition of embodiment is here, a set of stable and consistent constraints that are orthogonal to the agent's entire interactions. This sounds like what I'm talking about, It sounds like a very abstract statement. But, after many years of thinking, I reached this statement, which is a kind of a general definition of what essentially embodiment provides. I'll explain this later with examples. And another important aspect is that this constraints structures the interaction dynamics and gives rise to behavior and information. Some important keywords: orthogonal means it influences the interactions without specifying their contents. It doesn't specify output directly. For example, if I move arms, I move my arm like this, for example, hand trajectory. Hand can take an infinite variety of trajectory, right? But all these trajectories are constrained by the distance between the elbow and the wrist, right? This is always constant. So the entire infinite variety of this data points sort of obey this constraint. And hence, this structures imposes particular structure on the produced data. So this embodiment, in this case, is the distance between these two joints, but this doesn't directly specify any data, but it acts on all possible data, even data, it doesn't have to be within the given training data set or beyond or whatever, it doesn't matter. And it should be consistent with each other and the laws of physics and other universal laws. And it structures behavior, etc. I'll show some example here in the following slides. So let's take a very famous example in robotics. All the roboticists know this example. Let's look at the movie provided by the Cornell University group. And this is called Passive Dynamic Walker. It looks like walking very naturally, but you know that there's no computer, no sensors, no actuators, no batteries. Why it's moving? It's because it's a slope, you know. So the gravitational force is feeding the energy. However, you know, there's no control. Why this, you know, seemingly very natural movement? It's because of the result of embodiment. So the simple mechanism, the structure is like this. So you have two rods connected with a free joint here. And then at the end of the rods, you have plates, sole, you know, sole of the feet. That's it. And this simple structure constrains all the physical forces acting together, and the resulting movements are constrained by this structure and resulting in this particular pattern called biped walking, right? And it even has a stability, right? If you just push a little bit, it goes back to the regular state limit cycle. So it's a attractor dynamics. Okay? So this is a very typical, simple example of what embodiment is. It's a very simple structure, and this constrains the underlying physical processes and gives rise to the meaningful behavior, structures, the physical interactions. Okay? Another example, this is from our lab many years ago. Jumping robot, and again in slow. Quite natural looking jumping behavior, like a frog. But again, here is no explicit control. What we did is just, so we use pneumatic actuators, air muscles, and in the beginning, we exert the maximum power of all the muscles, and then it starts to jump, and then when it's flying, we turn off the muscles, all the muscles. That's it. But the resulting behavior was quite natural in that, for example, this one, horizontal axis is the time, vertical axis is the joint angle, and first the hip joint starts to move, and then the knees, and then the ankles. So this natural-looking ordering is emergent. And this is due to the body structure. For example, we use a biarticular muscle system, which is unusual in typical robotics, but very typical in animal bodies. For example, this muscle pulls this end here, and that end here, so pulling over two joints. So these two joints are sort of indeterministic, right? So typically it's tricky to control, but animal bodies adopt this kind of structure very often, and it results in adaptive capability. And anyway, so this kind of body structure and also other muscle mass distribution, etc., gives rise to the structures, the behavior. Okay. Another example, here's another robot. This is a humanoid robot from our lab. And what it's trying to do is starting from the lying flat in the ground, on the ground, and then swing up the legs, swing down, and in one action is trying to get up. what fails, right? So it's getting better. Please enjoy watching, and for strange failure patterns, and sometimes it exhibits a very dynamic behavior, like almost flying in an inverted posture, or etc. And it's getting better. But as you watch, you start to sort of sympathize with this guy, like so some part fell off, and then it gets closer, right? So okay, it's trying to stop hard, but failed. So now you're more and more sympathized with this guy through embodiment, right? So it broke its back. So we replaced the backbone and then tried again. It's succeeded. Okay. So what was I doing? So we were not just playing around with these expensive robots, but there was a whole bunch of theoretical discussions about control theory, etc. This particular movement actually is unsolvable analytically. If you write up a control equation, the differential equation of the system, and try to solve for the input, right, the control input. This is because this is an so-called under-actuated system. I don't go into detail, but so if you theorize this movement, it's really tricky and difficult to solve. But if you ask somebody who is a little fit, the guy who is good in sports is like this, very smooth, right? So humans don't care about the mathematical difficulty of this movement, right? And we sort of captured, the data, the motion capture, and then analyzed what the trick here. So this is a data in knee joint and hip joint space for 10 trials in different colors. You immediately notice a very strange structure here. Here, every time he does it, it's very different, right? Scattered. Here is very convergent. So why is this? So for robotics, immediately this is a puzzle, because when you control a robot, you sort of define a target trajectory, the ideal trajectory, and then do a feedback control so that the error is always minimized. Why this guy exhibits large error in some point and very small error at the other point. Now we analyzed this whole motion and then discovered this. At the particular point here in the state space, this is where the guy or the robot hits the ground with both feet, rolling, and then the feet hit the ground at that particular moment. We analyzed the possible trajectories for successful or unsuccessful postures. So this is, very tiny characters, but again, knee and hip joint space. And the red area is a successful state posture. All the rest, the blue areas are unsuccessful. So this means that very tiny region, this is a very strict condition for the posture at this particular point. If you fail in achieving that particular posture, you fail. So you cannot go beyond this point. This is very critical, but at this point here, a little before that critical point, where you're swinging down the leg and then you're starting to bend your knees to fold your legs. There's a trade-off between how far you swing down the legs and when you start to fold the legs. And this is a trade-off thing. And successful region in red is very large. Means there's a big margin here. So you don't have to be very strict at this stage how to do it. So this kind of thing. So in this whole task, there's a very sparse, important states along the state trajectory. And here is a very strict point. You have to really carefully achieve the particular posture here. But the rest of the state space, you have a lot of margin. So this band, the gray band, like river-like thing, is broad here, and then converges very strict here on one point, and then starts to widen here, and then converge, and things like this. This is the whole global state space trajectory shape. So what I mean is that, so we discovered this particular point and named it neck. And so it's like a neck of doing something. And this sparse important point emerges from this rolling body. There's no algorithm or data or anything. Here's only the physical processes. The human-like body interacting with the ground under gravity, that's it. And, but still, this information theoretic structure, the important state, localized, sparse, emerges from this process. And this is also important in sharing the information about this task, because when somebody is having difficulty with this task, I would just say, look, this is the important tip, so just mind about this particular posture, and then the guy would succeed. So this is like a symbolic information structure that emerged from embodiment that serves as a sort of basis for intelligent communication. So far, embodiment is a key to solving the problem of contemporary AI. That's my claim. And why? The AI had problems like these, not generalizable beyond training data set. I mean, of course, we accept to generalize, but we don't know exactly when it breaks. And it it suffers from the breaches in human alignment. So we really don't know yet how to completely assure human alignment. Now, the embodiment provides a grounding to the real world, of course. And moreover, it serves as the basis for open-ended intelligence because it doesn't specify the data itself, but it constrains all possible input-output relationships which go through the system. And it assures that all of these obey this given constraint. So I think embodiment and generalization of this embodiment idea could be an important key for approaching the problems in current AI. And moreover, human-like embodiment provides human-like structures on the interactions and accompanying information emerging from this. And so I think this structure is common to agents with shared embodiment. So it should support alignment and empathy and mutual understanding. Now, in my title, I said super-embodiment, which is basically about, by embodiment, we've been discussing in robotics about, the various things, but mainly on physical embodiment in its effect on behavior generalization, control, and also sensor information. But so now I think it's really time to generalize the idea of physical embodiment. And the first one is related to this. This is a work by Kohei Nakajima, who is my colleague. And this is his famous work using silicon rubber based object called the octopus robot. So it's like octopus arm, and it's swung by the motor. And what it's doing is like this. So the principle underlying here is, the idea here is that this structure is if from a physicist eye, it looks like a high-dimensional nonlinear coupled system, because virtually you can view that it's consisting of many components connected to each other, and then the connection, the coupling between the adjacent component is nonlinear, like a damper spring system. And then, so it's many of these elements, so it's a high-dimensional nonlinear dynamics. And then, if you add some sensors, bend sensors scattered over this body, you can read out the states of this. And then, this whole thing is equivalent to this high-dimensional nonlinear coupled system, which is a recurrent neural network. Right? And this type of organization, like you just input to this bunch of recurrent neurons, and then you get readout from some of these neurons, and then just do a linear network, so one-layer linear readout network, and then you just learn only this output one-layer weight distribution. This is extremely simple. You can do it in milliseconds, right? So, and you don't fiddle with the weights here. So you just adopt the sort of a random weight, right? Still, you can get a very enormous power of, for example, predictive capability of time sequence data. This is called reservoir computing. And the equivalent thing can happen here. So Kohei named this physical reservoir computing. And this movie shows that actually this leg is computing some mathematical functions like short-term memory task, parity checker, and etc. And actually, you can show that it does this computation. But anyway, important thing is that by this view, you can treat the physical body, nonlinear neural system, or even the environmental dynamics in the unified theoretical framework and apply the computational theory to this. So this is one way of generalizing embodiment, right? So one idea. Okay, next. Next important keyword is emergence. So before I talked about the embodiment, and it provides a structure in behavior, and also the information structure emerges from this. But to exploit that, you have to somehow drive the body in the beginning, right? What should we do? So if I drive the body in particular way, that's it, and the body move in that way, and that it's over. Should we use a GA or RL or whatever? It's not quite good because you have to assume certain parameters or state space or reward functions. So anyway, you have very limited search areas, and you bias the search, which is not good, because what I want is to explore the whole possible space of the structures of information structure that provides the embodiment, provided by the embodiment, and exploit it. So I want to avoid the bias. So what I first did is this architecture. So I introduced the chaotic maps. We started with the simple, this kind of equation, a variant of a logistic map. And what you do is feed the sensor value at one time point as x, and then compute this, and then output drives the motor. And you repeat it, just that. So, and you do it for different pairs of sensors and motors in a robot. And then what you expect is that the interaction between these chaotic dynamics takes place in the embodied dynamical patterns, dynamical processes. And the body is also interacting with the environment. So here, some process, I mean, well, I would expect that, some interesting thing would happen. This is like a really intuitive thing. But actually, there's some mathematical work behind this is inspired this work. So Kaneko and Suda's work in complex system science explore this type of mathematical structures. So they picked up a bunch of chaotic maps and then coupled them through averaging field and mean field. So, and then fed back to the input. And so this structure gives rise to very interesting complex patterns. So depending on the order parameters, the bunch of these maps exhibited partially ordered or completely ordered or completely asynchronous random-like phases, which means, like two of these synchronized together. The other three makes another group, and or sometimes all of them synchronize. And other times, everything goes random, depending on the parameters. This inspires so if you interpret as a robotic degrees of freedom, then it means that the robot would behave in a various coordination of different joints and limbs, right? So, and this coupling in this model is affected by the embodiment and the body-environment coupling. So it should exhibit some kind of embodied dynamical patterns. So anyway, so we did a series of experiments in this architecture, and this is one example. Here's a insect-like structure with 12 legs. Each leg is driven by one chaos map. And then, but there's no coordination circuits. So if you're familiar with the central pattern generator in vertebrates, typically you assume like phase relationship between the oscillators to impose a particular phase difference between the joints. But here we don't have, we omit it, So all the joints are completely independent, but they interact only through the embodiment, right? Only through the body, but as a result, some gate pattern emerges. Particular phase relationship immediately, like in a few seconds, emerges, and the robot starts to walk in particular direction. Right? So it's like an emergent, stable walking pattern, and it's even more than that. Like I said consciousness here, but it has a similar structures to the emergence of consciousness because these elements, all the elements independently starts some dynamics, and then they interact together through the shared body. Could be a brain, and then global pattern emerges, and then this emergent pattern starts to govern all the elements so that they are coordinated, and the coordination pattern maintains, right? So this is very interesting. And more than that, in this case, this guy hits the wall now. Now it hits. And then the gate it gets random. But in a few seconds already, it starts to walk in different directions. Right? So it looks like a sort of adaptive behavior. So it hits the wall, and it gets confused. But then it starts, it starts to move in a different direction, avoiding the wall. There's no sensor, no sort of central module that telling the robot to, change the way it moves or anything, and nothing like that. It's just complete emergent behavior. Now, it looks interesting, but strange, and what's it good for? Is it useful? Well, we stepped forward and then maintaining the similar principles, but the implementation in a more biological plausible way. So we introduced a neural oscillator, which is another new nonlinear oscillator. Now, it's not a logistic map, right? We use a BVP oscillator, but in the same way. So no phase relationship circuitry, but independently controlling each muscle. Right? The coupling takes place through the body only. And we also implemented the very primitive spinal reflexive circuit here to approach a little bit biologically plausible architecture. Now, and we tested it on a real robot, quadruped air muscle-driven robot. And it starts to move in various ways. It's not so fancy, It doesn't like do parkour or whatever, but still, it's amazing. It doesn't. The system doesn't know anything about how to move forward or walk or anything. Remember that the thing is just generating oscillatory signal to drive just one muscle. That's it. And then these systems sort of interact together through the body, and then some emergent behavior appears, and it's sort of walk forward or backward, right, and spontaneously changing. Right? So it's like this architecture is exploring what it can do with a given body, right? And it emerges from this simple mechanism, and this is called a very biologically plausible. In all vertebrates, you would expect for this kind of principles to be working, right? So it's not anything strange, right? And we applied also information theoretic analysis using transfer entropy to analyze the information flow, although there's no information signaling cabling here, nothing. But we discovered that there's actually a strong information flow between different muscles, corresponding to coordination of the muscles in walking, so information flow structure emerges from this embodiment. Now, the final stage. So being said all these, all of these things could be found in human embodiment as well. And I'm particularly interested in the very, very early onset of intelligent behavior cognition in humans. And if you take up a very early stage, and this is even before birth, in fetal period. Fetus starts to move like in 7 to 9 weeks of gestation. And at this stage, so the cortex is not properly formed yet. And the source of driving signals is mainly from spinal circuit, right? So you can expect a very similar situation as our experiment before. So then the baby body is driven like that, and then emergent behavior, and then this gives rise to the sensory motor experiences, and this will provide a structured information pattern on the developing brain, self-organizing brain. And then some structure is acquired on the developing brain, and then starts to drive its body. And then further complex pattern emerges. And this scenario is like a bootstrapping thing, and we claim that the body shapes brain. So the body gives rise to the important information structure, and the brain acquires it, and it self-organizes. So this scenario is experimentable. So we set off building a very precise physical body model of human fetus, like musculoskeletal data, in collaboration with medical doctors. And we built this pretty accurate body model of about 400 muscles, and also tactile sensors, Merkel cells distributed over the skin, the same driving circuit and the spinal circuit. And then also we built a brain model, the cortical model, based on the MRI data from the newborns. And we attached LIF spiking neuron with STDP learning on the cortical plane, cortical surface. And we integrated all of these to test our scenario. This shows the movement of the whole body movement within the simulated uterus with a liquid here. And this movement is generated by the spinal circuit. It's emergent, it's a result of the same principle. You know, the oscillators independently drive the muscles. There's no coordination circuit, but you know, they interact through the embodiment, including the uterus environment, including liquid, the resulting like natural-looking fetal movement. And then it gives rise to the sensory motor signals, tactile and proprioception signals fed to the simulated brain, which is learning. And so one result, this is a close-up of the somatosensory area. It shows a clear, distinguished body representation here. It's a result of learning. Interesting thing is this is the same area from a contrast experiment where it says ex utero. So we did exactly the same learning outside of the uterus, like this, in this. So we put the fetal model here, like in a flat bed, on a flat bed in the air. And it sort of failed to learn about its body. It was kind of an unexpected, interesting finding, but we analyzed the data, sensory data, and we discovered that the sensory data structure is very different depending on where the fetus is put. So in the uterus environment, strong correlational structure appears, whereas outside is less structure. So that's why probably the brain had a difficulty in learning. We discussed with this with the medical doctors, and actually this has some implications on raise the risk factor in low birth weight babies. I mean, preterm babies. So it's a hypothesis. We can say that shortened experience, sensory motor experience in uterus may has some effect on acquired body map. And the body representation is strongly related to the later cognitive development, even related to ASDs. So from there are supporting evidences from other research. And so this may be one possible factor for accounting for the developmental disorders. Anyway, so I have to really quickly skip to the end. So, well, this shows the brain model, but I skip. And we are further developing uterus models, more realistic, and trying to simulate mother-fetal interactions, etc. And we are also trying to explore the further development, continuously connecting to the afterbirth interaction with the caregivers, etc. And also we are interested in twin interactions. And there is a very interesting like proto-social interaction patterns. And when we try to simulate the afterbirth interactions in realistic environment with toys, etc., and humans, we built a baby robot with all tactile sensing, skin, and audio-visual sensing, and like attentional system. So the guy is interested in strange object and try to touch it. And through these interactions, we can collect realistic data for further brain development. Now, so far we talked about just the individual development, but of course, the social aspect, social cognition is the really important thing for humans. And actually, this is my family many years ago. And I don't have time to explain, but on one Sunday afternoon, we started to clean up the garden, and then the children took all different types of tools and started to do different things. And for example, this lady grabbed this thing and then swinging just like the mother. But it's fluffy and it's no good for sweeping. But this lady is really happy. So like this. And this guy grabbed the same thing as the mother and starts to really energetically swinging this thing. But this guy is scattering all the leaves around. So it's not fulfilling the shared goal, right? And this guy got this different sets of tools. They're doing completely different movement and posture, but serving the shared goal. Okay. So this is an example of imitation. But imitation in real world is about which aspect you think is important and which aspect you sort of assimilate with the target guy. This is the beginning of social cognition, I think. Okay, and sorry. In technical advancement in imitation, in robotics or AI, this is a result of deep imitation learning from our lab. So there are technologies that are necessary to construct action, understanding, and reproducing, generalizing from that, etc. This robot is doing a very precise task of needle threading, right? It's a very difficult task because the thread deforms and etc. There are particular technique model using a visual attention system to focus on the very important details, etc. This is a banana peeling. Easy task for humans, but very difficult for robots. Because the skin deforms and is a completely unpredictable thing happen, and still you need to degeneralize. Anyway, so there are technologies, and also cognitive scientific work, including us. So there are many scientific knowledge about action understanding imitation. But I mentioned moral and things like that, which means you should be able to judge what's good, what this guy is doing good or bad, things like that. This aspect is not very well, explored. And then I've been thinking about this for many years, and then finally hit some missing link from aesthetics, from the field called neuroaesthetics. Actually, it's about the judgment of good and bad, which is actually beauty or not. So in Greek philosophy, goodness, truth, and beauty are like treated as the equally as an important virtue for humanity. And goodness and beauty always comes as a pair. And when you see some scene like this and feel it's beautiful, it's not just a superficial beauty, but the behavior, this goodness of this behavior looks beautiful, right? So, and it's at the root of humanity. So there's actually a neuroscientific evidence for this. So neuroaesthetic research, particularly by the Shiz and Zeki, reported that the medial orbitofrontal cortex respond both to beauty and moral. So the brain, our brain, treats beauty and moral like equally, right? And also this part is also strongly coupled with the emotional system and a strong connection to the internal organs. So here, the link is established. So moral, beauty, emotion, and embodiment. In this case, internal organs. Right? And this is very natural. So when you see immoral behavior scenes, you feel it's ugly, and sometimes you feel nausea, etc. So it's a very natural thing. But now it's time to really construct a model for this. So Super-Embodiment 2 is before in robotics we talked about the musculoskeletal system, sensory and motor patterns, but here we should talk about internal organs, metabolism, etc., and connection to emotional systems, and probably the somatosensory hypothesis, somatic marker hypothesis by Damasio is very, very important. And so we set off building a model. It's complicated, but this is a model of a respiratory and cardiac system. We simulate the blood oxygen level, etc., and then how the brainstem controls the lung movement and cardiac oscillations, etc., and how they interact with the LC, and then the amygdala, and then cortical system, decision-making circuitry. So build up this system, and it's working like this. And so we are trying to reproduce some of the psychological data. For example, in this case, the emotional, you show emotional faces and then ask the participant to judge and push buttons. And then the data shows that it's biased by the respiratory phases, and our model basically can reproduce this kind of thing. Now, the final, but I'm running over time, but the most important thing is that, based on these and connecting to this recent reports by Professor Kanakogi at the Osaka University in Japan, they showed that preverbal infants, 6-month infants, so they don't yet speak, right, prefer just actions. So they prefer good guys, and then they even punish the bad guys. How they do that? They did it with the, by showing animation like this, and this is a bad guy, and hitting on this victim, and then this guy is looking at this, trying to do something, but can't because it cannot go out, right? And then finally here, oh, not yet. Sorry, a few more. So really aggressive, right? And here it's the opening, and then this guy comes into between to block the aggressor, so to help it. So this kind of movie. And then shows a slightly different movie without helping actions. And compared the looking time and etc., they established that the preverbal infants actually knows the difference, and they prefer the just actions. And also, there are techniques of using gaze. So the baby is looking, and first looking at the similar presentation. In this case, the green guy is the bad guy, aggressor. And then after that, the red point is the gaze point of the baby. So the baby very quickly learns how to use the gaze to punish the guy, So, yeah, so look, if you look at the bad guy, the stone falls and then can punish, right? So this is a very interesting method, but the baby can really quickly acquire this skill and then shows this. Anyway, so this is non-linguistic capability, and 6 months old. So we can say that this is different from linguistic world, and continue from body, sensation, motor, emotion, and continue from the story I've been giving, right? So we think that the embodiment can be extended to incorporate all these aspects, including internal organs and emotional systems and beauty, what's good and bad, and then finally to the really early sprouting of humanity, like moral. I'm not saying that this would be the ultimate solution for solving everything, but this is one way to address the in-principle way to address how the important moral, including also the open-ended intelligence, will be addressed. So the idea of super-embodiment is like this. So these are the 4 aspects of how to generalize embodiment ideas in my talk. And then this is a sort of a current hypothetical developmental pathway starting from body, the musculoskeletal aspect, and the internal organs, and then follow these 2 pathways towards integration into moral sense. We started the new project this April for 3 years, good scale project with all these guys, Ishizu, the neuroaesthetics guy, and Kanakogi, the guy who did this infant experiment. We collaborate on this to build a model of embodied emergence of moral. So that's the end of my story here. Thank you for listening.
Thank you so much for that really fascinating and engaging talk. I think we have time for just a couple of questions. We have some microphones here, so if you wanted to raise your hand, a microphone will arrive to you.
Yeah, thank you very much for the talk. Could you elaborate a bit as to where this infant morality is coming from? I understand they're embodied, they're interacting with their environment, and is it their sense of beauty that leads them to the punishment, or what is the link between these two streams?
Well, basically, that's a question we are asking. Still, we don't have a direct answer, but this is a hypothetical thing. So, based on the internal organs, it gives the baby the sort of the good state and bad state thing. Feeling good, feeling bad type of thing, and there's some early integration between the exteroception. So. You see some the hitting guys and things like that, and then somehow some empathy circuitry will reflect that input to the like self-sensation, internal organ responses, etc. So that's a mystery part. We have to investigate how. This connection is established. But we suspect there is some connection. And then once it's established, then we can say that this is a very early stage, very primitive form of, this moral responses. So I'm talking about a very, very early seed of morality, and not the full-fledged adult complex ones. But I'm interested in where it starts, and what we need for the system to sort of develop these capabilities.
Yeah. Thanks for that great talk. Here. Thanks. I was curious, do you think, given that this coupled system of the brain and body have the common goal of the survival, we can explain the interaction between these two systems based on something like reinforcement learning, like reward maximization? Do you think that's the case?
Sorry.
So do you think, if you assume that these two systems that are coupled to each other, according to your talk, have a common goal of maximizing the chance of the survival, so we can explain these interactions based on things like reinforcement learning?
You mean what? Still, I don't get the point. So the brain and body serve the same purpose of the survival, and through reinforcement learning,
we can explain the coupling between these two systems.
Coupling,
the interaction.
Coupling. Yeah, of course. The brain and body should be. It's always coupled, and in reinforcement learning, But still, which aspect of coupling are you talking about?
Maybe you can take it offline, because it's mine. I can take it offline.
Okay. Yeah. Sorry.
I think we should probably close the session now, but we have a coffee break that you can ask further questions to Yasu. So let's thank our speaker again.
Thank you.